Welcome back to POE. We're going to be talking today about calculating truss forces. Forces, we got two types of forces, compression and tension. With these then, at the top, imagine two forces pushing on either side, and that's when a body's being squeezed, that's compression. If you can take that object and really stretch it out, that would be tension. Truss is composed of slender members joined together at their endpoints. They're usually joined by welds or gusset plates. On here, I want to point out that right here are the gusset plates. That's what they're talking about. All right. So this one, I would say there's probably some welds in here, but the ones that I can easily see are the gusset plates. A simple truss. A simple truss is composed of triangles, which will retain their shape even when removed from supports. So up here at the top, one of the common mistakes that a lot of students make is they make these rectangles or squares. The problem with that is when you apply a force, the truss will just push over because there's no cross member, there's no cross support. So typically, you're going to find out that trusses are made from triangles, all right, and you can identify the triangles in the shapes. What this does now is this triangle keeps it from going right and left, and then this triangle, you could say, is what's supporting it up and down, or vice versa. Pinned and roller supports. Well, we've already talked quite a bit, not quite a bit, but somewhat about a pinned or a roller support. A pinned support can support a structure in two dimensions, right? And we use this symbol up here, which we've already used in class. A pinned support is not going to allow an object to go up or down because it's pinned in place. And it's also not going to be able to go right and left. Think of a pinned support kind of like a gusset that we showed from earlier. It's going to lock it in place. The other one here then is a roller support. A roller support can only support it one dimension. One direction is what I'll use. If we have it on the ground, it's going to allow or keep things up and down. It's not going to allow it to go down. But because it's a roller support, if it were to expand, let's say due to heat, it would be able to, right, to move left and right. It would be able to go left and right. We can also use roller supports when it comes to signs. A lot of times they'll put a roller support on the bottom, and basically that just keeps the sign a certain distance from the wall. Again, if the sign were to get hot and expand or contract with the heat or coolness, then it can roll up and down, right, up and down on the wall. All right, solving truss forces. All right, assumptions: all members are perfectly straight. All loads are applied at the joints. All joints are pinned and frictionless. Each member has no weight, and members can only experience tension or compression forces. Um, these assumptions are ones that we're going to make every time that we're doing our calculations. Automatically, these are the assumptions we make. We know that's not always the case. For example, each member will have weight. If you're using 2 by 4s, right, 2 by 4s obviously have weight. All right. Pinned and frictionless. Well, that's a pretty easy one to assume. For the most part, that's true, but there could be, as something gets older or poorly designed, poorly put together, or built, it could have some friction. Um, Members can experience more than tension or compression forces as well, but for the most part, when it comes to calculating, these are the assumptions we're going to make. Static determinacy. Statically determinate structure is one that can be mathematically solved. All right, this tells us if it's statically determinate. Um, J stands for the number of joints, M for the number of members, and R for the number of reactions. So that's going to be an important calculation that we're going to keep coming back to. In this one, a truss is considered statically indeterminate when the static equilibrium equations are not sufficient to find the reactions on that structure. There are simply too many unknowns. Well, in this case, we have two pinned. All right, so J again stood for the number of joints, M is members, and R is reactions. So as we look at this one then, J, there's um, joints. In this case, we don't have two joints. We have one, two, three, four joints. we have 2 times 4 equals the members. So we have 1, 2, 3, 4, 5 members. And then the reactions. Well, there's a reaction here. It's pinned. So it's going to have a reaction that goes up and down, and it's going to have a reaction that goes right and left. This is a symbol for a pin. So again, we're going to have those same 2 reactions. Well, I've got 1, 2, 3, 4 reactions. As you can see, this problem is not statically determinate. This is statically indeterminate. And what that tells us here then is this is pinned on both sides, and that's our number one problem. With it being pinned on both sides, would this bridge be allowed to expand or shrinking with the heat or coolness of a summer or season? Well, no, it wouldn't. So this one here is statically indeterminate. We get 8 equals 9, and they don't equal up. So what we'd want to probably do is turn one of these sides into a roller. So then we would only have one force up and down, not a right and left. And then that would change then our reactions. We'd only have 3. As you can see in the next drawing here, they've replaced this one over here with a roller instead of that pin, and it does make it statically determinate. Okay, here's another example. You can pause this and double check it, but you're going to find that there's 19 joints, there's 35 members, and there's 3 reactions. Now, the reactions you probably aren't going to be able to add up very well, but if there's only 3 reactions, that tells me one side is pinned and the other side is rolled, or has a roller. For a bridge to be in equilibrium, there's 2 things that have to happen. First of all, the moments have to have a sum of 0. We can't have one moment going in have a moment in either clockwise or counterclockwise. Otherwise, the bridge is going to move. It's not going to be very stable. We also have to have the sum of our forces in the x directions have to be 0, and the sum of the forces in the y direction also have to be equal to 0. Okay, the first thing we're going to do here then is we've got to make sure our moments are 0 for a bridge to be statically, or for it to be stable. Sorry, not statically determinate. So how do we go about calculating that moment? Well, again, remember that moment equals force times distance. So to be going about doing this, I'm going to take the sum of the moments, and they're telling us that it's pinned here today. We know that it's pinned here today because it's got 2 reactionary forces. So I've got a moment. First of all, I've got a moment that's going clockwise, and then I've got a moment here that's going counterclockwise. There is nothing up here at B this time, so that's a little bit different than yesterday, so it makes the problem a little bit easier. So the moments at A backtrack here a little bit. Alright, I have a moment here at D. The moment at D, and that's clockwise, so that's a negative, plus the moment here at C are equal to 0. Well, I'm going to take the moment of D over to this side, and I get moment of C equals the moment at D. Well, what do I have at D? I have force and a distance. Our distance is 3 feet, 500 pounds. So my force is 500. My distance is 3. On the left side of the moment at C, I have a force, which is my reactionary force, and it is a distance of 10 feet away. So to find what RCY is, I'm going to take 500 times 3, which is 1500, divided by 10, and get 150 pounds. So that tells me what RCY is. This is now 150 pounds of pressure pushing up. Well, common sense tells me that if there's 500 pounds pushing down, and that's 150 pounds pushing up, what is RAY? Well, I'm just going to real quickly here say that RAY plus RCY have to equal 500. And that's 150. So what does what does Ray equal? Well, some simple math, then it's going to tell me that RAY is equal to 350 pounds. So after calculating the moment, I've been able to not only find RCY, but once I found RCY, I was able to come back now and find RAY. The nice thing about RAX, it's pinned. So what does that tell us about our left and right forces? Well, that's what we'll be doing in our second part of calculating truss forces. Hey, I hope this has been informational. I'll catch you on the flip side.